Okay, so it was obviously a bad idea to just pad the message by appending something. So the only choice we really have is prepending stuff. So let's create a new padding scheme where we take our AES key and prefix something. This is, for example, FFs, FFs. So our message that we will encrypt with RSA looks like this. Oops, sorry. It's like this. Here's the padding. So just FFs. And this is our AES key. Is that a good idea? Well, as you probably know by now, no, it's not. We can use Coppersmith's attack. So Coppersmith says we can find small roots for a polynomial, fx 0 modulo n, without factoring n. That's very important. This attack uses an algorithm called LLL. It's a lattice-based algorithm that goes far, far beyond the scope of this lecture. If I decide to do a cryptography lecture, maybe I'm going to include the LLL at some point, but you just have to know it uses a specific lattice algorithm. So, or you don't even need to know that, I'm just telling you. So, how this works is we formulate a polynomial, fx, and we say, okay, the padding is this. We know the padding. This is a constant that we know because it was ff plus x we don't know. It's our AES key minus the ciphertext. And this here is to the power of e, so it's encryption. Now, take a moment and think about when does this polynomial vanish? Where does it have a root? Well, this polynomial has a root. It becomes 0 exactly at the AES key. If x is equal to the AES key, then the padding plus the AES key encrypted minus the ciphertext will be 0, since padding plus AES key encrypted is the ciphertext. So we can use Coppersmith's method to find the root for this polynomial, and the root of this polynomial is actually our AES key that we encrypted with with RSA. This is a full implementation of Coppersmith's attack. Well, it uses not Python this time, but Sage. Sage is a computer algebra system based on Python. We're not going to look at it during this semester, but this is a full attack. Here we create a polynomial, which is very easy to do in Sage. And Sage even offers this small roots function here, which uses LLL algorithm, and with this we can just recover the plain text, which is our AES key.